Right, so that's our setup. We don't care what the other registers are. When we're performing the fetch execute cycle, the only thing that matters is the program counter. The program counter is our key value. When we access interrupts and we have to go and service interrupt routines, the only thing that the CPU saves is the PC, so that it can carry on when the interrupts finish. You'll see that process when we look at that in a bit of detail. Okay, the PC matters, the others don't. The others are used temporarily. They're all temporary during execution and decoding. Okay, so let's just start. So we're going to do a fetch. So step 1, PC to MAR. So let me do it in a different colour. So 100 ends up in the memory address register. We then read from memory. Remember, we're looking at it like this in mnemonics, but it's actually noughts and ones. So we do a read, and it arrives at the memory data register. The control unit says, probably an instruction, because I've just started a fetch execute cycle, so I'll copy it to the current instruction register. At this point, it goes, I'm going to decode it. It decodes it, it goes LDA-4, that means immediate addressing 4. I can now increment the program counter. And it looks at that and it says, oh, I've got everything I need. I'm loading the actual value, the operand 4, to the accumulator. Bang. Finished. That's the execution of it. So if you're using immediate addressing, these are going to be the quickest instructions that the CPU can execute. It did a fetch from memory, it had everything it needed. There was no more waiting. Bang, done. They're quick. There are caveats to immediate addressing. You're limited to the size of the numbers because you've got your opcode and your operand, and they've got to fit in the instruction. So if you've got a 16-bit instruction format, you can't have a 16-bit number that you load immediate because you've got opcode bits and you've got the effective address bits. So you're limited. On a 68,000, there was a really compact form of the load instructions called move, which could do a 4-bit immediate value, so a number between 0 and 15. And it's surprising how often the number you want is between 0 and 15 when you're like initializing something. Okay, so there were quick, short instruction formats. It all starts getting messy, all that sort of thing now. Okay, so that was immediate addressing. So let's have a go at our second addressing mode, the one that Little Man Computer's got. It's called direct. So with direct addressing, that is where the operand is an address. So I'm just gonna carry on. I'm gonna write another program. So I'm gonna update my PC to 102. Don't care what's in the other registers, and I'm gonna have this LDA 103, and at 103 I'm gonna put the value 10. Okay, so direct addressing means it is an address. So we do our fetch. So I'll do this one in blue. So we put the program counter in the memory address register because that's how we fetch data, by selecting it first, the location. We then do a read. So we read, it comes across the data bus and it arrives at the memory data register. The control unit assumes this data, that remember we're abstracting this and looking at it in assembler format. It assumes that this number is an instruction, so it copies it to the current instruction register. It then decodes it, and it goes, oh, LDA 103, direct addressing. Oh, I've got to do something else. But it now knows how to increment the program counter. So it does that. And it goes, right, okay, now let's start getting all the data for this. So it says, I have got an address where the data is. So in order to access that address, we need to put its value in the memory address register. We can then fetch that data, and the data at 103 will arrive at the memory data register. Do not, as people do, automatically dump that value in the current instruction register. It is not an instruction, it's a piece of data. Right, at this point, the control unit can go, ooh, I've got everything I need to execute this instruction. So it can now execute it. What was it trying to do? Well, it can look back at the current instruction register and it can go, oh yeah, where was I? Oh yeah, I was loading a value to the accumulator. Well, I've got that value now, so it can go in the accumulator. What would happen if we carried on and did another fetch execute cycle? What would we execute next? 10, whatever that is. It's probably one of the coolest things you can do when you're low-level coding, is to write data that is instructions and manipulate data, or manipulate instructions by overwriting data. You can get some really nice compact solutions to problems, but they become impossible to debug. So it's not a recommended thing, but sometimes it is useful and handy to be able to do self-modifying code, as we call it. It's good for machine learning algorithms as well, although we do a lot of that at high-level language now. Right, that's direct addressing. So let's have a look at the one that is the infinite recursion system. What's the one where it's not an address, it's the address of an address? Indirect. So indirect. So let's just carry on. Let's do another program. So I'm going to set the PC to 104. I don't care what the other values of the registers are. So I'm now going to put LDA 105, and I'm going to put it in brackets, and that's just how I'm in my assembler denoting indirect addressing. Right, so at 105, I'm actually going to put 103. Okay, so we're going to try and execute this. So we're just going to do what we always do. We're just going to follow the fetch execute cycle. The control unit isn't doing anything intelligent. Don't let anyone tell you that CPUs are intelligent. They're not. They're the dumbest pieces of equipment we could ever make. They're no more intelligent than a nodding donkey that pumps oil. That they go do 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 do. Or like when Windy Miller is watching his windmill go round. Okay? There's no intelligence whatsoever. It's a process, and it's just a process that happens very quick. Right, so we start with the fetch execute. First step, we want to fetch an instruction, so the program counter, copy that over to the memory address register. Issue a read instruction, so the control unit does that by sending a signal down the control bus to say, oi, send us some data. That data will arrive at the memory data register, LDA 105. The control unit assumes it's an instruction, so it said I better make a copy of that into the current instruction register. Decodes it. It has a look at the addressing mode. It goes, oh dear, it's indirect addressing. This is going to be a pain in the neck. But now it knows how to increment the PC. So we go, right, increment the PC. It then goes, right, okay, indirect addressing. So 105 isn't my data, it's an address. So it goes and puts the address in the memory address register. And it says, read. So it issues a signal down the control unit, read. So we grab from memory, and it arrives at the memory data register. And the control unit goes, right, okay, what was it doing again? Looks back at its current instruction register, and it goes, oh, indirect addressing. 103 isn't the data. 103 is an address. So it puts the address in the memory data register. And it goes, right, that's where the data is. That's what I'm going to load. So we do another read from memory, and we get at 103, we've got a 10. So we load, that arrives at the memory data register. At this point, the control unit goes, yes, finally, I've got all the data I need for this operation. What was I supposed to do? Oh, load to the accumulator. So the 10 goes into the accumulator. Now, can you see with this one, what's quite interesting, when you're tracing, you can see how many fetches you did. How can you tell, what register can you look at to see how many fetches occurred? Yeah, MAR, excellent. The MAR has got 3 values in it, which meant we fetched from memory 3 times. So, unless you want to, indirect addressing is not the most efficient instruction format, because it requires 3 fetches. Direct required 2 fetches. Immediate, 1 fetch. So there's a cost. So once you start getting flexibility, but it's like everything in computer science, and we're coding, if you want flexibility, there is a cost. Execution cost for that. If you want rigidity, and you don't care about wasting memory, then you can eliminate a lot of these costs and do things in different ways. But it isn't something that you worry about too much at high level languages. We've got CPUs that can execute billions of instructions a second, so you don't really care about efficiency until you start doing something really complicated and really CPU hungry. Then you start worrying about these things. Okay, so indirect, the address of an address of the data, and you can see it physically there. Let's have a go at the last one, which was the indexed addressing. I've run out of colours, so I'm going to have to pick rainbow or something. My brain is going so tired. Indexed addressing. Right, indexed addressing. We're going to need to keep track of another register. And we're just going to call it X. So I'm going to put this code at 110 in memory. So I'm setting my PC to 110 so that I can execute this fragment. I'm going to first off set the index register. Oops. Then I am going to load to the accumulator a value from this little fragment of data. Okay. Right, so I'm going to go rainbow on there. Get this back. Right, okay, so we're going to execute cycle, so the control unit's just going to do its job. So we start off, we've got the PC, we need to access that, so we're going to transfer that to the memory address register. Very bizarre colour. That actually felt like I was having to press on to get the colours to come out. That's a bit weird. Obviously I didn't, but it just felt like that. It's psychological. Right, we then issue a read. So we're going to load the data that's at that location, and it arrives at the MDR. So this is LDX hash 0. We assume it's an instruction, so we copy it to the current instruction register. Can you see straight away that there's a little bit of setup required in order to access this array? It's a cost. It's a cost to get this flexibility. So it's only an initial cost though. Right, the control unit says, right, okay, let's decode it. Oh, load immediate to the X register. Fine, I can do that. So we can now update the program counter. Now it executes this. And it goes, okay, immediate mode, so that's my data I want to load. Load that into the X register. So it's got 0 in it. We check for interrupts, and then we go again. We go get the next instruction. Right, so it's 111. So we load that to the memory address register. We issue a read instruction, and then something arrives at the memory data register. And so in this case, it is LDA X112. The control unit says, I'll assume that's an instruction, so I'll put that in the current instruction register. So LDA X112. It decodes it. It goes, right, okay, this is index addressing. Right, now that I know that that's index addressing, I can update my program counter. Always try and get it in your heads about this, is that until we decode, we don't know how many bytes the instruction took. As soon as you start talking about memory addresses, you're talking about extra data. Okay? So, instructions end up being different lengths. So we need to decode before we can increment the PC. Okay, so we've decoded it, and we go, right, to execute this, I've got to get my data. And my data is obtained by combining 112 and the value of X. And then to access that location, that will have to go in the memory address register. How do you think that the CPU adds two numbers together? What component of the CPU gets involved? Yeah, arithmetic and logic unit. It's your maths maestro. Okay, so the arithmetic and logic unit adds these together for us. So we need to add them together. So we've got 0 plus 112. So that's what we put in the memory address register. Okay. Then we can go fetch our data. We've now got the location where it is. We can fetch it. So we look at 112, and the data that arrives at the memory address register is 12. We've now got our data, so we can actually execute. So we haven't executed this instruction yet. We've just been getting everything ready to execute. The instruction said load to the accumulator. So that's what we will do. So the 12 ends up in the accumulator. Now, if I'd have changed my program and I'd have crossed that out and put a 1 in the index register, we'd have ended up with 113, and we'd have loaded 14, and 14 would have gone into the accumulator. Okay? But that's it. So you've got these addressing modes. These different addressing modes allow you to access data in different ways. So it allows you to structure your code better. Anyone got any questions before I stop the vid on that?